Okay, so this is going to be an abbreviated version of what would be probably a few lectures in talking about these two things called the Biot Savart law and Ampere's law, which unfortunately I just feel that the mathematics are too complex for where we are at this stage, and I think end up being more of a distraction. And so as a department we've decided we're going to kind of brush those under the rug, but I'll still say something about it at the end of the video. But what we're going to do instead is kind of jump to the answers that you can get from doing something where you can actually calculate magnetic fields. Just saying that up front. So we want to ask the question, where does the magnetic field come from? We've been looking in the last couple lectures in terms of how moving charges respond to magnetic fields, but what is the origin of magnetic fields? And we can do it in this, we can do a simplified kind of version here where we're going to draw an analogy with the electric field. So the idea is, yes, I saw that my screen has died. This app has not been working in my favor today. So let's think of how the electric field was created and how and what responds to electric fields. We had individual charges Q, and we saw that they respond to electric fields, and we saw that they also created electric fields in that case. Similarly, let's think about magnetic fields. We've seen that magnetic fields exert forces on moving charges or currents. So by analogy, we find that currents or moving charges respond to and create magnetic fields. And this was kind of one of the big realizations that was kind of discovered accidentally. Hans Christian Ørsted was doing these physics demonstrations, with currents. And he noticed that when he had a little compass nearby one of his wire currents, that every time he had the current turned on in the wire, the compass would deflect. And so he made this realization, this connection, that while moving charges respond to magnetic fields, it also seemed that currents were creating magnetic fields as well. And so I want to look at just the answers that you get, and I'll point to a couple of YouTube videos that also show little demos of this. I assume YouTube would frown upon me kind of showing YouTube videos within a YouTube video, so I won't link them directly or show them directly, but I'll link to them that you can take a look at them. And the things I want to look at are 3 examples, and then I'll do some examples with them, and then I'll kind of do a little bit more elaboration on where all this comes from. So let's look at the magnetic field around a current wire, or a current carrying wire. That'll be the first of the 3 we look at. So in this case, here's my simple drawing where we just have a current moving in some direction down a wire. And again, this is a great thing you could do experimentally. You could take a little compass and hold it, around a wire loop, and you would notice that the compass does seem to deflect around the wire in such a way that if you were to do this with iron filings, you would get something that looks like this, where there's a current that is going, in this case, up through the wire. So I'll draw that. We have some current here, and it appears like that there is some sort of magnetic field that seems to loop around the wire. And the fact it's a loop is important. We've seen and have talked about with the bar magnet how there are no magnetic monopoles, and that everything with the magnetic field appears to be in the form of little loops. And we're seeing that again here. The magnetic field that appears around a wire appears to form some sort of little closed loop. Now the question then is, what direction is this magnetic field? If I look at the picture on the right, the iron filings have aligned themselves, but I can't tell you what is the north side and the south side. It's the positive and the negative direction. You want to think of that in terms of the directionality of the magnetic field. Well, of course, we could do the experiment where we could take a little compass that has a north and a south side and see how those two sides align. And we would find that, I'll do it maybe blue, that for this particular drawing, that we would find that the magnetic field is oriented this way. And then magnetic field out here also is a loop and is oriented that way. So what is going on is that we notice that the direction of the magnetic field, so that the E field is a loop around the wire. The direction of B is given by the right-hand rule. In this case, I think it's sometimes called the second version or of the right-hand rule, the one that we are more familiar with in terms of rotation. So if your thumb points along the current, then your fingers naturally curl in the direction of the field. So again, if I have this wire and I put my thumb to be in the direction of the current, then my fingers naturally curl in the direction of the magnetic field. And I can't point my fingers this way. Using my right hand, my fingers then naturally kind of curl around in the direction of the magnetic field in this case. Now, you would derive this by this thing called Ampere's law, but this is another great example of how you can use symmetry to argue what the answer should, what qualities the answer should have. Because now that I know that it's a loop, which again I can experimentally verify, I now have a sense of the direction. It's given by the right-hand rule. So again, if I had a wire that had current going the other direction, it would still be a loop, but the directionality would be in the opposite direction. Again, I'm going to point my finger along the direction of I. My fingers are going to naturally curl in the direction of the magnetic field. So it looks like it goes down behind the wire and then up in front of the wire, given by my right hand. And by the symmetry of the problem, if we're thinking of a very long wire, right, that it doesn't bend and it's not necessarily has a bend or changes direction, anywhere nearby, so that we can approximate it essentially as an infinitely long wire. It makes sense that the symmetry, just like how we saw for the electric field around, along a line of charge, that the symmetry, the magnitude of the magnetic field is only going to depend on how far away you are from the wire. So that we can quantify this, let me draw another. And if I want to know the magnetic field at this location, the only distance that matters is this distance here, which I think we were using capital R for the electric field. So let me follow that notation again. That distance from the wire is all that matters. And when you actually do the calculations, you get that the magnitude of the electric field is equal to this new constant, mu naught, times the current, divided by 2 pi, and then this value of R. And this mu naught is called the permeability constant. And it is playing an analogous role as epsilon naught did for the electric field. Epsilon naught was kind of a constant that quantified, the electric field in terms of whether, in terms of the medium that it was present within, whether it was which could be a vacuum, could be air, could be something else. This constant does the same thing, but for electric fields, for magnetic fields. Mu naught is defined to have a value of 4 times pi times 10 to the negative 7. And then I forgot to write down what its combination of units are. I could just figure it out, of course, because I know that this entire thing has to eventually have units of force. So it's going to have, well, let me just figure it out, of course. I should be able to practice what I preach. So then the units of mu naught better be the unit of B times the unit of R divided by the unit of I. So then this is going to have units of something like Tesla, meter per ampere, something like that. And then you could write those in SI units if you want. And maybe I'll bring those up just so that we can have that. Yeah, looks like newtons per ampere squared is how we want to write that as well. Which isn't technically an SI, but that's okay. So here's one result that I want us to kind of be knowledgeable of and be able to do calculations with. Around a long wire, the magnetic field does get weaker as you go farther away. That's the 1 over R. It depends on the strength of the current and then some overall constants. The directionality is determined by the right-hand rule. So for example, looking at this example right next to where I've highlighted, if I were to ask what is the direction of the magnetic field at that point, at this point here, if I imagine putting my thumb along the direction of the current, it's going to curl up out of the page above the wire, and then my fingers are going to pierce back into the page below the wire. So then it looks like B at this point is going to point into the page. And above here, B is going to point out of the page in this region, and then into the page in this region. The way to look at it is what if I had, say, a current that is moving out of the page at this location. So at that point there, imagine a long wire coming in and out of the screen. Again, by the right-hand rule, if I then hold my thumb pointing out of the screen, my fingers for my right hand, despite what the mirroring of the camera might look like, it then curls around that location. So then it looks like by the right-hand rule, the magnetic field is then oriented in this direction. And the strength depends on how far away you are from the wire. So that's one. That's a good example for us to do. And again, there'll be some YouTube videos that show some kind of iron filing demonstrations of this, kind of like the picture I just showed. So the other example is that of a coil. A coil of wire. So in this case, this might be a wire that then loops around once, might loop around multiple times, and then there's a current that then is flowing through that coil. And I'm curious to know what is the magnetic field around that coil of wire. This could also loop around multiple times, so it could be that it loops around kind of once, twice, 3, 4, 5, and then eventually goes around. But let's just focus in on one and then see how it might extrapolate for others. So in the videos, you'll see that it looks something like this. There's a magnetic field that kind of comes up and comes down, kind of loops back around. And again, you could use a little compass to get the orientation. And on this side, it kind of does the same thing. And close to the center, kind of does something similar, and then eventually loops back around. And this might look familiar. It kind of looks like the same magnetic field that we had for a bar magnet. And historically, actually, it's actually very important that this has the same magnetic field as you get when you hold a permanent bar magnet up, in terms of the study of the origin and reasonings for magnetic fields. But the fact that it's a dipole, we can then ask ourselves, what is the strength? We can get a sense of the direction. It essentially looks like a dipole magnet. And so, what about the directionality? How can I understand the directionality? So let me just draw the coil of wire again. And again, the current is coming in this way, looping around, and then going back out. And notice again, this is given by the right-hand rule. If I have my thumb pointing along the direction of the current anywhere in that coil, and I imagine curling my fingers would curl up through the circle, but then loop back around on the outside of the circle. So my fingers are curling up through and then loop back around and go down on the side, and then curl back up, and I can do that again on the other side as well. And again, try it out for yourself. Just imagine, you might even be able to find a ring or something that if you put your thumb around the direction of the current anywhere along that ring, your fingers will curl up through the ring and then loop back around on the other side. And if the current's moving in the other direction, you should be able to get the same sort of thing, but with the magnetic field flipped. Yeah, so again, try this on your own. What if you had a coil that looked like that and did that? So then it goes that way and that way and that way. You should be able to convince yourself that the magnetic field does something like that in terms of its direction. Again, use the right-hand rule with your thumb in the direction of the current. So now what I want to do is think about the magnitude of the magnetic field around this coil. We can already, and I'm going to focus on one particular region, which is the axis along the center of the ring. So if I draw, I can draw a straight line on that. If I imagine kind of putting an axis with the ring, with the center of the ring at the center. Show it curved. Like that. Then I could ask, what is the magnetic field along this particular axis? And maybe we'll call it the z-axis, where the ring itself has a radius of radius r. With the current, I'll have it be going in this direction. So we know that the field lines look like what I drew up above, kind of curling up from bottom up by the right-hand rule. By the direction of the field lines, I know that along this particular axis, the field is always going to point straight up. And then if I switch the direction of the current, it's going to point straight down. Then when you work it out, it turns out that the magnetic field along this axis is given by mu naught over 2, and it's multiplied by the current times r squared, and the entire thing is divided by this quantity parenthesis z squared plus r squared. It's all being raised to the 3/2 power. So, not unlike things that we saw with the electric field, where you have these kind of square root things going on in the denominator. It's actually the same exact sort of form. Now, and again, this points straight up, so I'll put C, right? If the quantity you plug in for I is a positive number, then this is pointing straight up, given by the right-hand rule. But again, don't get confused by the vectors, right? Because you can always use the right-hand rule to figure out the directionality. Then this can give you the magnitude, right? I might even just make that explicit, right? The magnitude is that. And the direction is given by the right-hand rule. In this case, it points straight up. If the current was going the opposite direction, it would point straight down. And so then you'll particularly see that the magnetic field at z equals 0, well then if I plug in 0 for z, I get mu naught over 2, and it looks like it's I r squared, all over r squared to the 3/2 power, r squared to the 3/2 power. It's the same thing as r to the 3 times 2 over 2 power. Notice that's just the same thing as r cubed. So then that's mu naught over 2 I r squared over r cubed, or the same thing as mu naught over 2 I over r in this case. But then that's right in the center of the ring. Then I'll let you work it out for yourself. The magnetic field, at let's see, evaluated at z much greater than r. So imagine z is enormous. When z is enormous, that denominator simplifies. Z squared plus r squared is essentially just z squared. Right? I have $1 million and I add a penny. I essentially still have $1 million. So the z squared is what lives at the end of the day. And this becomes mu naught over 2. Then you have I r squared, all divided by what ends up just becoming z cubed. And note the units still work out because you have r squared divided by z cubed. That still overall has units of 1 over distance. So the units match for these two examples. Right? You have 1 over distance in this case. R squared over z cubed still has units of 1 over distance. It's not that the units are lying to you. Now another common application of this coil is that you'll have a coil of multiple loops. So I'll draw it so we can kind of see the individual loops. So you might have it loop around n times. So loops n times around. Now in this case, you can think about what you might expect. When you had one of those coils looping around, we could argue by the right-hand rule, kind of the direction of the field, and we got a magnitude for the field directly above what I just wrote down. Now imagine you had 2 loops on top of one another. If the current is going in the same direction for both, which it is, then they both are creating a magnetic field that are adding together. Each loop is creating a magnetic field that comes up like this, loops around, and then comes back up through the bottom. So if you loop around n times, you're essentially creating the same magnetic field n times, and they're all adding together. So in this case, then the magnetic field, the magnitude at least, is given by mu naught over 2. But instead of just I, it just then becomes n times I, r squared, over z squared plus r squared to the 3/2 power. Nothing about the directionality changes. If we're approximating essentially we call it a flat coil, all the coils are essentially on top of one another. All right, last one I want to show, then I'll do a couple examples, is the solenoid. And I think the video that shows the coil also does the solenoid if you keep watching. Now this is similar like a coil where you're going to have a current loop multiple times, but we're going to have the loops stack on top of one another rather than being crushed down into the same location. So a solenoid might look something like you have a current that comes in, and then it loops around, but it has some sort of physical extent as it loops. And then eventually the current comes out the other side. Usually, they are usually way more spaced. They're usually essentially right next to one another rather than having these big gaps between them. But there's some sort of n loops over some length L. Right, the wire loops around n times, and notice if you think about the direction of the current is always going in the same direction. So it comes up, kind of goes down in front for all of these loops, and goes up in the back for all of these loops. Again, kind of messy to write. Well, essentially the current is always doing the same thing in each loop. And again, that's going to play an important role because then that means that essentially we're going to get fields that add together in some spaces, and then fields that more or less cancel out in others. I think it's easiest to show this if I do a cross-section of this solenoid. So imagine taking the entire thing, and I'm just going to slice it right down the middle, so that we have the cross-section of all the wires on top, and the cross-section of all the wires on the bottom. Where, if I follow the picture I have on the right, the current is coming out of the page on the top, and then it's going into the page on the bottom. If I use kind of a faint gray, right, again, kind of the loops of the solenoid are kind of doing this in front. And then they do the same thing in the back. So we can ask ourselves, what do we expect the field to look like outside and inside? Well, again, we can use the right-hand rule. For all the top ones, for all the currents at the top, right? Imagine what the magnetic field is from those little tiny pieces. It's coming out of the page, so again, I'm going to have my thumb point out of the page, and then my fingers curl around the direction of the magnetic field. So for say this particular wire, the magnetic field is going to be doing something like this, in a counterclockwise direction by the right-hand rule. Similarly, this particular one is going to have, by the right-hand rule, something that goes in the counterclockwise direction. This one has something in the counterclockwise direction. Similarly, for all of them. So what ends up happening is that when you add all of them together, what you get is essentially a big loop that goes around by the right-hand rule in the counterclockwise direction. And if you go a little bit farther out, and what you get is, where you get farther out is you get, again, something that kind of looks like a oval sort of thing. I'm not drawing it super well, but that's okay. Now let's think about what's going on with all the wires at the bottom. So then those wires loop around, and now they're going into the page. So again, if I stick my thumb into the page, my fingers are curling around in the clockwise direction. So as a result, I'll do it in red. In the clockwise direction, those wires are creating a magnetic field that kind of looks like that. And then if I draw a little bit bigger circle, then we have something that also looks like this on the outside. I know this is a little hand wavy, but you might be able to see what's happening here. If I look on the inside of the solenoid, so if I look at what's going on kind of in between the wires, so what's going on here, notice that the magnetic fields are all adding together. There's a positive superposition of all those magnetic fields. Versus on the outside, this red magnetic field is being canceled out, at least partially, by that blue magnetic field. Similarly, this red magnetic field here is being canceled out at least partially by that magnetic field up there. So what ends up happening, or what we call an ideal solenoid, I didn't realize I was out of room, so let me plop that down there. That for the ideal solenoid, what we have is that there ends up being a uniform magnetic field inside, and no magnetic field on the outside. Essentially, all of the magnetic fields by symmetry kind of add together to create a uniform magnetic field within the solenoid, but then they all cancel each other out because they're going in opposite directions, the blues and the reds, in my diagram on the outside. And so what ends up happening is that you get something that kind of looks like this. If this is the solenoid, and again we're going to a cross section, you have a magnetic field that's uniform on the inside and is 0 on the outside. Now of course when you're near the edges there are some fringe effects. As long as you're not really close to the edge of the solenoid, this is a very, very good approximation. And again, the video that shows this with the iron filings, you'll see that when they turn the magnetic field on, only the iron filings inside the coil seem to move, where all the ones on the outside essentially do not budge at all. Again, demonstrating that the magnetic field does exist in between the coils, but is more or less 0 on the outside. And again, if there is n loops in a length L, this is often combined, and I can call little n as capital N divided by L as the loops per unit length. How many loops per inch or whatever exists within the solenoid. And then the magnitude of the magnetic field ends up just being mu naught times I, the current that's going through all these wires, times little n, the number of loops per unit length. Or if I want to write it with the capital N's, capital N divided by L. Or again, L is the length of the solenoid in this case. So if you loop it very finely together, right, you can get a very strong magnetic field. Or if you have all the loops kind of very close to one another, small l, that gets you a strong magnetic field as well within the solenoid. And then the direction, again, is given by the right-hand rule. Again, I think the cross-section is kind of the easiest way to visualize it. Right, so if you have this cross-section where it's coming out of the page on the top into the page on the bottom, by the right-hand rule, the magnetic field should follow the directions I've drawn here with the arrows. Again, for me, I might take my thumb pointing out of the page on the top, then to curl my fingers around into the solenoid, my fingers are pointing to the right. Okay, let me do a couple examples, and I think I'm going to call it because I've suddenly started to also not feel very great. So let me do a couple examples. Let's imagine you want to measure the magnetic field near your microwave, which has some long coil of circuit that attaches the microwave to your wall. So you have some wall outlet that you then have a wire that then attaches to your microwave. This is the wall. Now actually what's inside that wire, right? We've been thinking of kind of wires as kind of unidirectional, right? That the current flows in one direction down a wire. But, in an actual wire that connects to your wall outlet, there are actually two wires in there because it has to complete a circuit, where you have some device, think of it like a resistor, and you have to have something that some wire that comes into it and then some wire that comes out of it and then attaches, in this case, to some power supply through your wall outlet. So really what this has is you might approximate as having some wire on the top, which then has some current going that way, maybe with a current of 10 amps. And then there's also a wire on the bottom. Put it on top. There's some wires going on the bottom that takes the current out. That's going out in the opposite direction. And it might be that let me move this over, that the distance between these two is something like 0.5 centimeters. And I want to ask myself, if I were to measure the magnetic field near this wire, I now know that a current creates a magnetic field. Do I have to be concerned about being too close to this wire? So what if I'm located, say, at this point here, which is going to be a distance, I'll use gray, a distance of about 3.3 centimeters. That is too hard to read. So it's going to be a distance of 3.3 centimeters from the red wire, which means then the blue wire is a little bit closer to that point. What is the magnetic field? And I want to know magnitude and direction. Well, let's think qualitatively first. The red wire is coming in with current going to the right. So by the right-hand rule, if I stick my thumb along the red wire, the magnetic field is then going to curl around in circles around, or in loops around that red wire. So it's going to come out of the page above the red wire and then turn around and go into the page below the red wire. So at this particular point, I expect that B is going to go into the page, or at least the B that's being contributed from the red wire. If I think of the blue, it's then going to be the opposite. My thumb points to the left, my fingers point into the page on the above the wire, and then curl around and come out of the page below the wire. So then that should then be pointing out of the page. Now, do they cancel perfectly? No, because they are different distances from this location. So to see which one wins out, I'm going to define out of the page as positive and into the page as negative. I then know that the total magnetic field is going to be the sum of the blue magnetic field plus the contribution from the red wire, or which I'll call the red magnetic field. And so in this case, I'll write down in symbols first and then plug things in. Let me call this 3.3 centimeters R naught, and then this width here, W, this 0.5 centimeters. Which of course I should make sure everything is in SI units before I start plugging things in. But in symbols at least, the blue, which is out of the page, we're going to take to be positive, is going to be mu naught. I guess I can stick with my color conventions. It's going to be mu naught times I, which is going to be 10 amps, divided by, looks like 2 times pi. And then the blue is a little bit closer, so it's not R naught, but it looks like it's R naught minus W. And then the red looks like it's negative mu naught times I, all divided by 2 pi, and then just R naught. That's not too bad. I could factor a bunch of stuff out to make my life easier, right? So it looks like I factor out mu, I, 2 pi, and what's left, it seems like it's going to be 1 divided by R naught minus W minus 1 over R naught. Then making sure I convert to meters, right? So R naught would be 0.033, and then W would be 0.005. I plug all those things in, and I get about 13 microtesla at the end. And I'll explicitly say positive 13 microtesla. It's positive, which means overall it points out of the page, and that makes sense. If you look at, since it depends on how far away you are, and it gets weaker the farther you are away, the red wire is farther away from this point, so it's a little bit weaker than the blue. So since blue is pointing out of the page, it slightly dominates over the red, but to this very small value, much smaller than just the ambient magnetic field on the surface of the Earth. By several orders of magnitude. So we don't have to worry too much. Let me do one example just to show, really make clear the vector nature of the magnetic field. All right, suppose I have a 2D plane here, and I have, suppose at this location, this Y value, I have a long wire of current that has some current I. And then at the origin, I also have a wire that's going in and out of the page. And suppose the current is coming out of the page with some current, same magnitude I, say, just to make the math a little simpler. And I have some location, which I will call, so let's see, let's have the red wire be a distance y above the axis. And then there's a point here, a location x. And I want to know what is b at the point x comma 0, which will be a contribution of these two magnetic fields. I have two wires that are contributing to the magnetic field at that point. I should be able to write down in vectors what's going on. Let's look at the blue wire first. The blue wire, again by the right-hand rule, thumb points in the direction of the current, and it seems like in this case then the magnetic field is going to loop around in a clockwise direction. So at the particular point x comma 0, I expect it to be pointing straight up. So I could write that down. The blue, I expect to be pointing straight up, so I have mu I 2 pi, and then I'm going to write it as a column vector this time. Why not? So it's pointing straight up, the x component is 0, the z component is 0, and then the distance from the wire is just x, so then it's plus 1 over x in that case. This magnetic field only has a y component, right? Don't confuse that it only depends on the x to mean it has an x component, right? It depends on the value of x, but it has only a y component at that point. Then, if I look at the red wire, right-hand rule, thumb along the arrows, fingers curl around. It's going to curl in front of the wire and then up behind in the back. So in that case then, it looks like, if I imagine where it is at that dot x, it's going to be pointing into the page at that location, which we will take to be the negative z direction. So then at this location here, looks like it's also mu naught I over 2 pi. And then the components, it's pointing into the page. There's no x, there's no y, and then negative 1 over y in this case. It has a component in the z direction that depends on that distance away from the wire, which in this case is just y. So then the total magnetic field looks like it's mu I over 2 pi. And the components of the vector looks like it's 0, 1 over x, negative 1 over y. And that is the 3D magnetic field at that point. Last one. And this one I have a demo that I will show in class. Suppose I have two wires, and they both have current and they're running, and they don't necessarily have to have the same current, so I'll say I1 and I2. But these are parallel to one another. Parallel wires with current in the same direction. I want to think about the forces that they exert on each other. So they each create a magnetic field. And let's draw it. They're both going in the same direction, so then by the right-hand rule, the magnetic field looks something like that. And then for this one, the magnetic field looks something like that. So they each are creating a magnetic field that the other is in the presence of. We also know from last time that there is a force exerted on a wire if there's a magnetic field in the region. What are these forces, and particularly, let's think about right now just the direction that they point. Then in class we'll work out some actual magnitudes. So the force on I1 from I2, we know quantitatively is I1 times the length of the wire cross the magnetic field that it is within. Again, not the magnetic field it creates, but the magnetic field it's within. So I might call this B2. It's the magnetic field created from wire 2, the one that has current I sub 2. And similarly, F on I2 from I1 is I2L cross B1. And let's have them both be the same segment of wire length. So again, we're just going to focus on direction for this example. You'll work out the magnitudes in class. Now, each of these wires are creating a magnetic field that has a formula, right? Mu naught times I divided by 2 pi r. The direction is given by the right-hand rule. So let's ask ourselves, on wire I1, the direction of B2 at wire I1 points in what direction? So I'm looking at the blue magnetic field, right? So the blue magnetic field by the right-hand rule, my fingers come out of the page above the wire and then circle around and go into the page below the wire. So the direction of B2 at wire 1 points out of the page. So, I'm going to have to move this down. So then I have the direction of the current is pointing to the right. That's I1 or L. And then I have the magnetic field is pointing out of the page. So then the force, the direction at least, is the cross product of them. So the cross product of, I start with my fingers pointing towards the right, I then curl my fingers so that they point out of the page. The force points down. Then if I go back here, looks like the force on this wire points downward. F on 1 from 2. Now what about for the opposite wire? If you're thinking Newton's third law and it should point up, extra credit point for you. But let's figure this out using the forces as well, the magnetic force equation. So the direction of B1 at wire I2, so I2 is going to the right, and then, if I think by the right-hand rule, my thumb points along the direction of I1, the magnetic field curls out of the page above I1, curls around and goes into the page below it, so then it points into the page. So then I have, for the bottom wire, the current is moving to the right, the magnetic field is going into the page, the cross product, fingers point along I, curl towards the position of B, my thumb points up. F points up. And it looks like I have two arrows that are pointing towards one another, F to 1. So then it seems like we're seeing that parallel currents attract one another. And so, and you'll work out in class, opposite currents, or anti-parallel, I guess, opposite currents repel one another. This is kind of interesting. If you have two currents side by side that are going parallel in the same direction, is really what I should say, right? Parallel currents meaning in the same direction. They end up attracting one another. Where if you have two currents and one of them is going the opposite direction, they repel one another. Maybe I'll just tease one of the answers. Let's do the parallel. So we set up this device where, do not try this at home, please. We essentially have two wires here that will have current going through them in the same direction. So both of them will have current going through them in the same direction. And essentially what I'm doing is I hook it up to a car battery, which again, don't try this at home. And you'll see I'm going to essentially touch the car battery, one of the nodes of the car battery, to this device, and you should see them react once current starts flowing through them. So no current flowing through them, then I'm going to touch. Notice they snap together. Let me do it again. So notice on the left, that yellow thing there, that's my hand about to touch, and send current through the wires. And when that happens, boop, look at that. You can also see that it gets really hot on the left there. See that? See all that? Ooh, that's why don't try this at home. So that's two currents in the same direction attract. Why not, since we're here? Let's do the going in opposite directions. So then when they're going in opposite directions, I've essentially switched the chords around a little bit. And so then when I play it and I touch them together, they repel. There you can even see a spark. Why do I do this? Right, then they fly apart from one another. Boo. All right, maybe I shouldn't do that in class. Yeah, I'll do it in class. All right, so there we have opposite currents are repelling. In this case, it was parallel currents in the same direction attract. All right, and we'll work out some of this more math in class. But again, the idea is that we're going to take these answers of what the magnitude of the magnetic field is. So if I go back and do some highlighting, right, we had for a long wire, those were most of my examples came from that. We have the magnetic field along the central axis of a coil. And then we have the magnetic field within a solenoid. We'll use those, and you might have even already used some of them in lab to work through some more examples, especially when we now move on to induction.